Okay, so for the first part of the module 3 here is you have to understand about how the data is represented in the computer. So basically you have when you have the and you have the decimal and binary representation here. So basically every number you normally use in decimal system. Decimal system, that means you have the base 10. Base 10, what does mean? That means for each digit you have the 10 value, right? So we think about for each of the digit you might have everything from 0 come all over to the 9 here. That is the decimal system. That decimal system, it's a base 10. Base 10, that means each digit you can store for the 10 number. Right? But actually in the number system, it can use any base. It can be by 2, by 3, by 4, by 5, by 8, whatever. You can use anyone. And normally in the computer, they work with the binary system here. So by 2, that means you understand about the definition of bit, right? The bit here. So basically in the computer, everything is processing is bits. Bits, that means one digit, you only have the two values, 0 and 1 away. 0 and 1 away, or they call it the binary system, or the by 2 here. The by 2 system here. And also you can have the other this system that uses computer. They are octal, it's a by 8, or hexadecimal, it's a by 16 here. Now think about the base and exponent here, right? So basically in order to represent the base and exponent, you can think about this one here. 10 raised to power 2. That means you have the 10 times 10, right? And you see the base here is the number 10, and the number 2 is the exponent here, right? And if you have the think about this one here. If you have the 5 raised to power the 6, so the 5 here is the base, and 6 here is the exponent. That means you have the pi times pi times pi times pi times pi times pi, 6 of them together, right? And remember one thing here, exception here. So whatever number it is, when you raise to power of 0, you only have number 1. But if you have 0 raised to power of 0, it is undefined. Right? So just remember one thing here. Any number not 0, when you raise to power of 0, you only have the number 1. Okay? That's everything about math. I do not want to go into detail here. Now, we learn about the decimal system. Okay? The decimal system is that for each digit you have the 10 value, everything from 0 to 1, and it break it down in the column here, right? Break it down column. So you see, you have the decimal system. You have decimal system. That means you have the base 10. You have base 10. That's why the first column here you have the 10 and raised to power of 0. You have the second column. You have 10 raised to power of 1. And 10 raised to power of 2 and 3 and 4 and 5 and 6 and so on here. Right? You see, you have the 10 raised to power of 0, you have the number 1 here. Right? You have 10 raised to power of 1, you have 10, you have 100 and 1000 here. That's why they call this one here the 1 column, the 10th column, 100th column, 1000th column, and 10,000 column, and so on here. Okay, so here is that thing. It depends on the position of the number. So think about, if you think about, you have the number 55 here. So see, they have the same number, pi and 5 here, but the value is not the same, right? The value is not the same. This one value is a 5, but this one here in the 10 column, actually it's a 50 here, right? The value of this one is 50, and the value of this one is a 5. So basically, when you look on the into the system here, you have to understand about the position value also, right? So even that the number is a number 5, but the value is 50 here. So that is everything about the decimal system. The reason you have the 10 raised 10 here, 10 is right here, because each digit you have everything in the value from 0 come all over to 9. So 0, 1, 2, 3, 4, 5, 6, 7, and 8 and 9. You have the 10 digit here. Now you mentioned about computer. Computer works by 2, right? So the by 2, the by 2 here, the binary, the by 2. Okay. Now the by 2, it follows exactly the same, the process here. The only difference is that, you see, the only difference is that the base here is that of by 2. Instead of by 10, now it's a by 2, right? Because it's binary. For each digit, you only have the 0 and 1 only. So see, we break it down in the column here. So see, the first column, you have 2 raised to power of 0, 2 raised to power of 1, 2 raised to power of 2, 3, 4, 5, 6, 7, and so on here. Right? So basically, in the computer, you just group 8 bits together into 1 byte. Right? You have 1 byte. You have 1 byte here. You have 1 byte. That means you have 8 bits here. Right? That's why you see everything in the from 0 to the 7. You have the 8 bits or 1 byte here. Right? So see. For this one here, for this column, is the value of this column here. 2 raised to the power of 0, you have 1. 2 raised to the power of 1, you have 2. You just double it, right? You have a 4, you have 8, you have 16, you have 32, you have 64, and you have 138 here. Right? So the same, it follows exactly the same with the decimal system. The only difference here is the base. Now, instead of base 10, you have the base 2 here. So the thing about the same, if you have the number 1 and 1 here in the binary, you see, this one here, the number is the same, but the value is not the same, right? Value for this one, it is number 1, but value for this one is the number 2 here, right? Okay, value is the number 2 here. Now, know about the process of the binary here. So how we convert the binary number to the decimal? You follow exactly the same as this one. Think about if I have the number here, if I have the where am I? If I have the binary number here, you think about I have the number 1, number 0, number 1 and 1, 0, 0 and 1 here. So how I convert this 8 bits here into the decimal number? Now how I do it? I work exactly the same. I add them up together, right? See, you have number 1 here, and the value of this column 128, right? You just count together. You have 128 here, and you have this one, the number 1 and 64. Column, right? You have the 64 here. This one I have 0. This one I have 16. This one I have 8. This one I have 0. This one I have 0. And this one I have 8. And I just add them up together, right? So when I convert 1, 1, 0, 1, 1, 0, and 0, 1 here, I have 192. I have 208, right? 208. I have 208. I have 216. I have 270 here. Right? That is the way you convert from the binary to the. Is that correct? 192, 192, and 208 here. Okay. So that is the way you convert from the decimal. Sorry, that's the way you convert from the binary to the decimal. Make sense? It's very simple, right? But the only thing you need to understand that you have to understand about the position here, value here, right? The first column, number 1, the second, 2, 4, 8, 16, and 32, 64, and 128 here. So when you understand the position number, it's very easy to convert it from the binary to the decimal. Okay, so you think about this one here, right? You think if you want to convert this one, you see, you have number 1 here. You have number 1 here is, sorry. You have number 1 here. 1, 2, 3, 4, 5, 6, 7, 8, right? So you have number 1 is the column 128. This one, 64, you have 0 here. This one, 32, right? This one, you have the 16. This one, you have 8. This one, you have 4. And this one, you have 2. And this one, you have 1 here. So we add them up together, right? Add them up together. You have 128. You have the 32. You have 8. And you have 2. You add them up together. And you have 170 here, right? Okay. I go with very fast with this one. It's very simple here. But the only thing you need to understand is that you have to understand about the value of each of the column when you convert it into the binary here. Okay, that's the thing. But how you can convert the decimal back to the binary? How you convert it? So basically, in order to convert the decimal to binary, you do the process. You do in the reverse way. You do it in the reverse way here. So think about if you want to convert the 172 here. If you want to convert 172 here back into the binary, so you only have to work from the left to the right. Work from the left to the right. So see, in order to make it up for 172, I need 170. Sorry, I need the 128, right? So that's why I put the number 1 here. So when I only have the 128 here, I minus 128 from that. I minus 128 from that. I have the 44 left, right? I have the 44 left. Now I have the 44 left. I move to the right. In order to make it the 44, I do not need this one, right? That's why I have put 0 here. In order to make it 44, I need 32. That's why I put number 1 here. So when I have the 32, I have to minus 32 here. I have 12 left. When I have 12 left, I move to the right. I do not need the 16. That's why I put 0 here. In order to make it for the 12, I need 8, right? That's why I put the number 1 here. Now I need 8. I have 4 left. 4 left. I move to the next one. It's exactly matching here, right? So see, I minus 4. I have 0. That's why I have 0 and 0 here. All right. So when you convert 172 to the binary, you have 1, you have 0, you have 1, 0, 1, 1, 0, and 0 here. Okay. Any question with this one? Hello? You have any question, guys? Can you hear me? Do they hear me? They cannot hear me?
Yeah, I can hear
it. Okay, so we learn about the decimal system. We learn about binary system, right? Now we learn about hexadecimal system. So hexadecimal system is a base 16. Base 16, that means for each digit you have the 16 value. So basically, you see, you have everything in the hexadecimal system. You have everything from 0, 1, come over to the 9, and after that you have A, you have B, you have C, you have D, you have E, and F here. So we can think about A is the 10, B is the 11, C is the 12, D is the 13, E is the 14, and F is the 15. Right? So see, if you have everything from 0 come all over to the 15, that means you have the 16 value here. Right? That's why they call it hexadecimal. Hexa, that means you have the 16 here. Okay, so when you work the hexadecimal system, okay, it follows exactly the same rule. It works with the column here, right? So see, the first column here, 10 raised to power 0, you have number 1 here, right? That's column 1. The second column here, 16 raised to power 1, you have the 16 column, right? And for this one, you have 256 column, and this one you have the 4096 column, and so on here, and so on. Okay, so see, again, you break it down in the column, right? You see, now it's a hexadecimal. That's why you have the base 16. You have base 16, you have base 16, 16 here, right? Column, see, you have the 16 raised to power 0, you have the column 1. You have 16 raised to power 1, you have the column 16. And you have 16 raised to power 2, you have the column 156, and so on here, right? So now what happened here? If I want to convert from the hexadecimal to the decimal, think about I have number B2 here. What do you think? What is the value of the number B2 in hexadecimal when you convert it into the decimal? What is it? What do you think? What is it? Now, can anyone give me the answer? When you convert B2 in the hexadecimal into the decimal, what's the value? Now, in order to do that, you have to understand what the B in the decimal system. 0, 1, 2, 3, 4, 5, 6, 7, 9, right? A is a 10, B is 11, right? So basically, E here is 11, and 11 here in the 16 column, right? So we have to time together, but so basically, this one you have 176 here, right? 176 here. 11 times 16, you have 176, right? And this one, you have 2, and you add them together, you have 178 here, right? So basically, if you have the B2 in hexadecimal, and if you convert it into the decimal, you have 178 here. Make sense? Make sense or not? Huh? Okay. So what happened if I give you another example here? If I have the 3E here, what's the value of 3E in the decimal? 3E in the decimal. Yes.
62.
62, right? Okay, so we see you have 16 and 3, you have the 48 here, right? And E it is 14, right? A 10, B 11, C is 12, and D is 13, and E is 14. Right? So see, 48 times add them to the 14, you have the 62 here. That is correct answer. Right? Make sense? Okay. So that is the way you convert from the hexadecimal to the decimal here. So see, that's the hexadigit. You have everything from 0 to 15. You have A is the 10, B 11, C is 12, D is the 13, E is the 14, and F is the 15 here. So that's why you have the range everything from you have to range everything from 0 come on over to 15. That means you have the 16 value, and that's why they call it the hexa. Hexa, that means you have the 16. Okay, so yes, you know how to convert, right? You know how to convert from hexadecimal to the decimal already. But how you convert from decimal to hexadecimal? So basically, it works exactly the same, right? You do everything from the left to the right here. You do everything from the left to the right. So think about if you want to convert 800, you see, if you want to convert 875 into the hexadecimal here. So how we do it? See, you work everything on the column here, right? So see, this one is column number 1, this one column 16, this one column 256, and this one column 4096. So you work everything from the left to the right. In order to make it up for the 875, I do not need this one. I put 0 here, right? I put 0 here. So in order to make it for the 875, I need the 256. I need 3 of them. I need 3 of them, right? So that's why I put the number 3 here. So when I have the number 3 is that what when we time it back together, you have the 256 here. You have time 3, you have 8 here, you have 6 here, and you have 7 here, right? You have the 768. So we have to subtract it. You have to subtract it from the 875. You have to subtract to this one, right? So what do you have left? What do you have left here? Okay, you have 107 left, right? You have 107 left. So now we move to the second one. Of course, in order to make it for 107, you need 16, right? And you need 6 of them. You need 6 of them. So 6 of them, you make it up for the 96 here. Right? So we have to minus 96 for this one. So what do you have left? You have 9 here, right? Sorry, you have 11 here, right? So that's why you see B here is 11. Right? So when you convert the 875 from the hexadecimal, from the decimal come to the hexadecimal, you have the 3, 6, and B here. Make sense? Okay. Okay, so when you convert the hexadecimal to number, so you will break it down in the column here, right? You just add them up together, right? Okay, so in some case, if you can use the hexadecimal notation. That means you see you have everything in the decimal here: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 15 here, right? So you see it matching together here in the decimal. 0 is the same, 1 is a 1, 2 is a 2, 3 is a 3, 4, 4, 5, 5, 6, 7, 8, 9. But 10 is 8, right? 11 is a B, 12 is a C, 13 is D, 14 is E, and 15 is F. And of course, when you convert decimal 0, you have the 4 bit of 0 here, right? And so on here. So see, in order to represent for hexadecimal, you have the 16 value, right? You have 16 value. And in order to represent 16 value in the binary, you need a 4 bit. You know that, right? You need a 4 bit in order to represent hexadecimal. You see, you have one bit here. You are able to represent the two value 0 and 1. And you have the two bits. How many value you can represent? If you have two bits, how many value? 4, right? And you can write it 0, 0, 0, 1, 1, 0, and 1, 1. And you have 3 bits. How many value you can have?
16.
Huh?
16.
No. 3 bits. How many?
6.
No.
8.
Yeah, right. Yeah, the things that why 8 here. I see. You have 1 bit, you have the 2 value, right? You have another bit, you have 2 value. You have another bit, you have 2 value. You see? Time 2 times 2 times 2, you have 8 here. So now you think about for the hexadecimal, you have the 16 value. You have 16 value, and of course, in order to represent 16 value, you need 4 bits. Because the thing here, 1, 2, 3, 4, 2 here, 2 here, 2 here, 2 here. Come together, you have 16. So that's the reason. In order to represent hexadecimal, you need 4 bits here. Everything starting from 0 and come over to F here. So when you convert this one, you have the 15. That means you have F here. Okay. Okay. So basically, here's a formula. If you have, here's a formula here. If you have n bits, so basically you have total 2 raised to power of n value. That's all. If you have n bits, you have 2 raised to power of n value. That's all. Okay, so yeah, it is common to write a long binary number in the hexadecimal notation here. So the 15 hexadecimal digit represents all combination of the 4-bit binary number, right? Whatever it is, whatever hexadecimal is, I only need the 4 bit in order to represent it here, right? So how we convert the following binary to the hexadecimal notation? So basically, you see, you have the long list of the binary here. So if you want to convert it into the back into the hexadecimal, you just group 4 of them together. That's all. Every hexadecimal you need 4 bits. That's why you group them together. Group 4 of them together. Group 1 here. Group 4 of them together. Group 4 of them together. And group 4 of them together. So see, if you look it back, if you look in back in the table here, you see F here matching with the E, and you have the 1 0 and 0 1. Actually, when you can convert it into the decimal, it's A here and so on here. So basically, in order to convert binary number to the hexadecimal, you just group every 4 bits together. That's all. Make sense? Now we learn about the integer representation, right? So you learn about the decimal, you learn about the binary, you learn about the hexadecimal also, right? So now, how can computer store the number, integer number here? So think about if you install program, right? You have to enter the number of dependent, right? So we think about you enter the number of dependent 5 here, number independent number 5 here, right? So you might raise the question, when you press the number 5, how computer store it and how it store it in the memory here, right? So that is the way we work with the process here. The integer number store and process in the quite different manner from the floating point. They are not the same. Floating point, you have both of the decimal part and the fractional part, right? But for the decimal point, it is the whole number. Sorry, for the integer, it's the whole number only. You have no fractional part here. Okay, and now the thing here, if you look on this one here, the integer can be stored at the unsigned number. Unsigned, that means you have no negative part, it's only positive. 2, 3, 4, 5, 6, 7. You have no negative. That is unsigned here. Unsigned, that means you have the only 0 and sorry, all non-negative here. Or it can store in the sign number. Sign number, it can be positive, it can be negative, or it can be 0. Right? So it can be stored negative 5 or 0 or number 10. Okay, so floating point also we have the sum of the several variation in the computer. Now, in order to using the integer in the computer, you have some of the format here. The first one is the unsized integer format here. The first one is the unsized integer format. The computer process the information from byte, and byte are normally stored in every 8 bit, right? Byte every 8 bit here. So basically here, if you want to store the 1 and 1 in binary here, actually, if you want to store 1 and 1 in binary, and if you want to store 1 0 0 0 0 1 here in binary, you have the same length at the byte, because it's only processing the byte here. So how it works? In order to make it up for the 1 byte, that means 8 bit here, right? They insert all of them 0 before that. So 1 2 3 4 5 6 7 8 here. Here, one more, right? So in order to store 1 on 1 here, you need to insert the 6 0 before that to make it up for the 1 byte. Right? And for this one also, we have 1 2 3 4 5 6. You need 2 more 0 here. Right? So you see, in order to store 1 and 1 and 1 0 1 1 0 here, both they have the same length, and you have to make it up to 1 byte. And how you make it up? You just insert 0 before that one to make it up for the 8 bytes. Sorry, 8 bits here. Make sense? Okay. So this is the core, is the unsigned form of integer. Unsigned that means non-negative. It can be 0 or positive only. It cannot be the negative here. Now, unsigned binary integer is very simple. You just convert it, and you know how to convert from the decimal to the binary here. So think about this one here. If I want to store the decimal number 10 into the 8-bit memory location, so the first step, I have to convert 5 into the binary. So if I convert it 5 into binary, I have 0 1 and 0 here. Now, if I want to store it in 8-bit memory, I have to make it up 5 0 before that in order to make it for 8-bit here, right? So that's why I have to insert 5 0 here before that one. So that is the way the computer store for the unsigned binary number of the number 5. So whenever you enter the number 5, and if the computer want to store it unsigned binary integer in the 8-bit here, it will store the whole string here into the memory. Now think about this one here. If you want to store the decimal number 928 here in the 16-bit memory location, again, you have to convert it into the binary. You have to convert it to binary. And you see, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's why you have to make it up to the 16 here by insert 6 0 before that. Okay. Now, what happened here? If I want to store the decimal integer in the 8-bit here, what do you think? What happened? In the 8-bit, I cannot. In that case, they call it the overflow. Because you see, I convert it, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 already. Have no way to store it in the 8-bit. That's why in the case they call it the overflow. Okay, that's the overflow here. That's the overflow. Okay, so if you think about this one here, if you store the decimal integer 23 in the 4-bit memory location, you cannot do that. It's called, you see, with the 4-bit here, it's a 4-bit. In total, you have 2 raised to 4. You have everything from 0 to 15 only. You cannot, right? That's why in order to store the number 23, you need you think about you need the 8-bit here. So of course, the more byte you have, the larger range it is, right? The larger range is a higher range in order to store the number here. Okay, so think about this one here. If you want to store number bit 8, it range everything from 0 to 255. Right? The thing is that why 255? Because the thing is that on here. You have the 8 bits, that means you have 2 raised to the power of 8. You have the 256 value. And you see, ranging everything from 0 to 255, it make it up for the 256. And if you have a 16 here, you have 2 raised to the power of 16. You have the 65,536, and everything is ranging from from the range here, right? So if you look on the number bit here, you can see what the range of the number you can store, right? So think about this one. If you want to store the number 300 here into the 8 bit, you cannot do that. You cannot do that because this one only ranging from 0 to 255. Okay, and okay, so that is the first thing. That's the first way the computer store the number, right? So that's the first way the computer store unsigned integer number. Anti-integer number is everything non-negative number, right? So what happens if you want to store the size and so you have the multiple way to do that with the computer. And the first format is if you want to store the size and integer number, you can use the size and magnitude format here. So it's a simple method to convert the decimal integer into the binary and represent the positive integer 0, right? So see, in the case if you have non-negative, you just normally convert it. You just normally convert it and store it here. Now, we also need a way to represent a negative integer number. So one way to do that is the size and magnitude format is one way to do that here. So how it works? If you work with the size magnitude here, in the case if you work with the size magnitude, format here, the leftmost bit is reserved to the size. The leftmost bit is reserved to the size. So if the leftmost bit is 0, it is a positive. And if the leftmost bit is number 1, it is a negative. That's all. That is the work with the size magnitude here. And every other bit, they call it a magnitude. That means you can think about the absolute value. Right? So think about here. So we can think about, I have the number here. I have 0, 0, 0, 0, 1, 1, 0, 0 here. And if I store it into the size and magnitude format, what do you think? What is the decimal number of this one? What do you think? What is the decimal number of this one? If I store it by the size and magnitude format, what is the decimal number of this one? 20. How?
Because the 0 makes it positive.
Yes, 0 here makes more positive, right? That's a positive. Right? So see, that is column number 1, right? This is column number 2, that is column number 4, and that is column number 8. Right? Is that double it, right? Okay, so see, you have 8 here, you have 4 here. So actually this one, you have the positive 12 here, or this one. Right? Make sense? Now see, when you work with the binary, you have to remember about the column value here. Right? You see, the first column 2 raised to the power of 0, the second column 2 raised to the power of 1, the third column 2 raised to the power of 2, 2 raised to the power of 3, and so on. Right? That's why it's only double here. You have 1, you have 2, you have 4, you have 8, you have 16, you have 32, you have 64, and you have 138 here. Make sense? Okay, that's the way you convert it. Okay, now that if you represent 0, 0, 0, 0, 1, 1, 0, 0 in size and magnitude format, you have the positive 12 here. That's the correct, right? Now, what happened if I have the number here? 1, 0, 0, 0, 1, 5, 1. Yes, what is it? What is the decimal number for this one? What's the decimal number for this one? Yes, right, right. See, the first mode bit here, the first leftmost bit is the size, and it's number 1. That means it's negative, right? Now you convert this one. Let's see, you have the 1 here, you have 2 here, you have 4 here, you have 8 here. You see, you add them up together, right? You have 8 and 2 here, you have 10. Right? So this one, when you convert this number, you have negative 10 in size and magnitude format. Make sense? Okay, so the size magnitude is very simple. The size magnitude is very simple here, right? So basically, if you want to store, think about this one here. If you want to store the decimal integer positive 23 in the 8-bit memory, right? So in the case of the positive, you just convert it normally, right? You see, in the case positive, you just convert it normally and you add 0 at the beginning. That's all. I add it by 0 at the beginning here. See, when you convert it here, when you convert it into the binary here, right? You want to make it up for the 8-bit, right? and 7 bit is the store for the magnitude here. That's why you have 1, 2, 3, 4, 5. You have the 6 and then 7 here. Add 0 before that. Now the leftmost bit it is a sign, and this is a positive. That's why you add 1 more 0. That's all. Right? Okay. Now in the case of the negative, in the negative also forgot about the negative. Sorry, in the case of the negative. Okay, in order to convert it, you just skip the sign first, right? You just convert 19. You just convert it 19 here. You have this one. 1, 2, 3, 4, 5. And if the 16-bit memory, 16-bit memory 5 only, so you need 11 more, right? But of course, you only need 10 more here. You only need 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it adds up. This one is the magnitude. This one is magnitude. And the last one here, you have to put number 1 because it is negative. Right? Okay. So that is the way the computer store for the sign and magnitude integer number here. But you have one problem with the sign and magnitude problem here. What it has? That is a problem of the 0 here. Now think about this one. If I have the number here, if I have number, if I have the number, this one, 1, 2, 3, 4, 5, 6, 7, 8 here. If I have number 8-bit number 0 here, what's the value of this one? What's the value of this one in the sign magnitude? What do you think? What do you think? Why 1? If I have 8-bit of 0 here.
0.
Yeah. So see, you can calculate it here.
0.
Yes, 0. The leftmost bit here 0, right? That means positive, right? And everything here 0 here, it's a magnitude is 0. So basically, this one is a positive 0. Right? You can understand that? Yeah. Now we can think about this one. Of course, positive 0 is 0 here. Right? Now what happened if I have another one here? Yes, this one. I have another one here. So what do you think about this one? What is the decimal number for this one? Negative 0, right? You see, that is side here, negative, and magnitude here 0, right? So you see, this one here. If I have this one, it's negative 0, or also it's 0. So you see, for 1 digit 0, you have 2 ways to represent it. In the second in the case of the sign and magnitude here, that is huge problem, right? That is huge problem with the computer. It's very confusing here. So basically, the computer do not use it doesn't use a sign and magnitude. That they write it here for you understand the process only, right? So the problem here is that you have 2 ways to represent number 0. That's why they do not use a sign and magnitude in the computer. So how we can overcome with this one? They come with the idea of another one here. The second one complement format. That's it. Okay. Now they come with the idea of the one complement format here. So the fact that 0 has the 2 possible way in the sign magnitude, and is why the reason is not only used, they have to use a different method to present the sign integer here. There are 2 other formats that may be used to store the sign integer. The first one is a one complement method here. Okay, it's not often used. You know why it's not often used later here, but you need to understand in order to explain, because you have to understand the process of the 2 complements here. So what is a one complement? Complement binary digit that you actually flip it. So if you have the bit number 1, you flip it, you have the bit number 0, and you have 0, you flip it, you have the bit number 1. That is complement. That's the process of complement here. That's all. So in the case of the one complement method here, the positive number represent as they would be in the sign and magnitude format. So in the case of the positive, it do it normally. You just convert it normally, and then you add 0 at the beginning. You do exactly the same with the sign magnitude. You do exactly the same with the sign magnitude. But in the case negative here, in the case of negative, right? You convert the number 6 here. You have 0. So you have 1, 0, and 0 and 1 here. Now you flip it. You flip it. That's the one complement, right? You flip it here. So it's flip it. You have 0, you have 1, and you have 1 and have 0 here. So see, in order to store it in the 8 bit, right? So you need 1, 2, 3, 4, right? You need 3 more 0. Right? And the leftmost bit is a negative. That's why you have number 1. That's all. That's the way you work with the one complement. So again, in the case of the positive, it works exactly the same. Right? Positive is very simple. You just convert it and add 0 at the beginning. That's all. But in the case of negative, you convert it into the decimal. You flip it. Sorry, I make a mistake with this one. I explained it by mistake. You convert it into the binary and you flip it. And the last one, the sign as the leftmost bit, it is the number 1 because it is negative. So how it work? So how it work with the one? Sorry, this one. What time is it? I think you should take a short break. I talk too much. Okay, so let me go on with the one complement here. So it's because you convert the 37 here into binary, right? So see, if you work with the positive, it's quite simple. You convert the 37 here into the binary, right? You have 1, 2, 3, 4, 5, 6 already, right? 6. Now, to make it up for the magnitude, you need 1 more 0 here, right? That is 7 bits. Now, you have to start the 8 bit. So see, that is a positive, right? So the 8 bit here, you have 0 here. That's why when you convert the 37 here and you store it into the 8 bit memory for the sign magnitude for one complement, it's always the same. And later on for the 2 complements also, it's always the same. If you convert the positive, it's always the same, right? So that is the way you convert in the positive here. Now, that is the positive, right? That is the way it's positive. Now, what happens if you have the negative here? So in the case you work with the positive, in the case you work with the negative, right? You convert the 37 here, that into the binary, right? So see, you need to store the 8 bit, right? Now you need the 7 bit in the magnitude. Again, you need 1 more 0 here to make it 1, 2, 3, 4, 5, 6, 7 here, right? So now you see, this one it is a negative 37 here. You have to flip every bit. You have to flip every bit in the magnitude here, right? So see, you have to flip it here. When you flip it, you have 1 here, you have 0, you have 1, you have 1, you have 0, you have 1, and you have 0 here, right? You have to flip it. And the last one, the leftmost bit, of course, it is the number 1 because it is a negative here, right? So that's why when you convert negative 37 here into the one complement, you have this one here. You have 1, 1, 0, 1, 1, 0, 1, and 0. Make sense? Okay. So basically, you see, later on we learn about the 2 complements also. But if you have the positive number, it's always the same. You just convert it normally. You add 0 at the beginning. That's all. All right. But in the case of the one complement here, if you have to work with the negative, you have to add 0 at the beginning and you flip it, right? You flip it and you add number 1 at the beginning. It is the sign of the negative. Now, if you look on the, if you remember in the case of the sign magnitude, right? Sign magnitude, you have problem 0 here. So see, in the one complement also, you have the same problem. You have the same problem here. Now, you have the same problem here. Okay, the problem of the 0 again. Now think about this one here. If you work with the one complement, what is this? What is the value of this one? 0 again. Right? You see that it is a sign positive. Right? That is the magnitude here. So you see when you have the positive, you just convert it normally. Right? That's why you have the positive 0 here. Now, what have to happen with this one here? Happen with this one. Now, if you look on the leftmost bit, number 1 here is a negative. Right? So see, this one is negative. Now, when you know that it's a negative, that means you have to convert every other bit here. Right? You have to convert every other bit. So you see, you have flip it here, 0, 0, 0, 0, 0, 0, 0 here. And of course, this one is 0. Right? So that's why you have 0 here. You see, for this positive 0, you have 8 bit of number 0. But for negative 0, you have the 8 bit of the number 1. Okay, you have two ways to represent the number 0 with the computer, right? So that's why computer, they do not use the one complement here. They raise here only for you to understand the process of two complements only. Make sense? Okay, now we work with the two complements here. Two complement integer here. So to find the to find the two complement of x number here, if the number positive, work exactly the same. You just convert it exactly the same. No. It depends, right? If you store it in the 8 bits, of course, the range everything from 0 to 255, right? But if you store in the 16 bit, you have huge number here. Now come back to the come back to my slide here. Here, see, you see that's what, right? If you store in the 8 bit here, it's stored 8 bit, you have you can store it for the 2 raised to the power of 8, that means 256 bits only, right? But of course, if you have the 16 bits, that means 2 bytes, you are able to store it to the 65,000 and so on here. And of course, if you have the 32, you have the 4 million here, and you have the 64, you have huge number here. I don't know how to pronounce this one, trillion or whatever. Huge number, right? So it depends on the memory. If you store it in 8 bit, the range is very small. But the 16 bit, 65,000, 32 bit, 4 billion, and 60 bit, huge range here, right? Okay, make sense? So it's not always limited to the 256 only. It makes sense, Daniel?
Not yet. If I consider 8 bit,
yes,
and the left is for the sign, it's still 256.
Okay, yes, that's the question. That's the correct question here. So basically, if you have 8 bit, of course, it's only limited to the 0 to the 255 only. That is the case of the inside here, right? But in the case of the side, you have to break it down into 2 half, negative and positive. So basically, it's a range from the 127 to come over to 127. That in case of the sign and magnitude or positive, one complement or two complement. If you work the 8 bit, of course, that's the range here. You cannot go over that. If you go over that, you have the overflow. Make sense?
Okay, thank you.
Welcome. Okay, now two complement integer here, right? To find the two complements of the x bit number here, if it's a positive, that convert it normally. That convert it normally and insert 0 before that, right? And insert before that here. Now, if the number is negative, convert number into the binary and find the one complement. Right? That's the first step. That's why we have to understand also the concept of one complement, right? So now, if the number negative, the first thing you have to convert it into binary and find the one complement. That's the first step. The second one here, add a binary number 1 to the one complement of the number. So when you convert it to the one complement, you add it to the number 1. You add it to number 1 here, right? And if the result is each bit more than x bit, you discard the leftmost bit. That is the process you can overcome the problem. Two ways to present number 0. I'll explain it later. Now think about this one here. Okay, sorry. The first thing you have to understand the process of adding number 1 here. So how we adding number 1? You can think about this one here. 0 is always the same, right? You have 1 plus 0, you have number 1 here. But you have 1 plus 1, you have 1 0. And do you know why it's 1 0? 1 0, you can think about this one here. 1 and 1, you have number 2, right? And this one, sorry. This one here, you have 0, and this one converted, you have number 2. Right? So that's why you have 1 plus 1, you have the 1 and 0 here. 1 0 is actually the 2 here. So how it works here? Think about this one here. Now think about think about this one here. I have 1 and 1, right? I have 1 and 1. I have 1 0 here. That means I have 0. I have carry out 1 for this one. Right? I have carry out 1 for this one here. Again, I have the carry out for this one. So see, I have 0 and 1. I have 1. And this one I have 1. Make sense? Now see, think about this one. If I have 1, 1, 1, and a plus 1 here, what do you think? What I have? What I have for this one? What do you think? In binary, I'm talking about binary.
1 0 1.
So see, 1 and 1, you have 0, carry out 1 here. 1 and 1 again, you have 0, carry out 1 here. And 1 and 1 again, you have 0, carry out 1. That is the way you add it. Make sense? That's all. You will see, 1 and 1, 0, carry out 1. Again, 1 and 1, 0, carry out 1. And 1 and 1, 0, and you have carry out 1. Make sense? Okay, that's the way you adding the binary order, right? And of course, 0 and 1 is have 1. That's why it's equal. Okay, now how we work here? How to find the two complements of 8-bit binary here? Think about this one here. If I have the positive, now the positive, again, remember if you work the positive, it only follows the same. It only follows the same. It's a sign magnitude whatever, 1 complement or 2 complement. It's always the same, right? You just convert it into the binary, and you want to work with the 8 bits, right? So insert 0 before that. That's all. 1, 2, 3, 4, 5, 6. So only 2 0 here, right? So this one, it is a positive number of the 43 in 2 complements, and you can see it works exactly the same in the 1 complement or sign magnitude. It works exactly the same, right? Now, what happened? You have the positive, negative here. Negative. The first step, you have to convert it into the 1 complement, right? So see, for this one here, in order to convert it into 1 complement, I take from this one here, right? I take it from 1, 2, 3, 4, 5, 6 already. So I need 1 more 0. I have 1, 0, 1, 0, 1. Now, in order to work with the 1 complement, I have to flip it. I have to flip it. That's why I have 1, I have 0, I have 1, I have 0, I have 1, I have 0, 0 here. And the leftmost bit is a negative here. That's why I have number 1. So this is the 1 complement. Now, in order to find out the 2 complements, you have to add 0. Sorry, you have to add 1 to that, right? So that's why I add 1 here. 1 and 0, I have 1, and so on here. So that is the way you represent the negative 43 in the 2 complements here. Make sense? Okay. Now, you go along the way to the 2 complements to understand that how it can solve problem 2-way 0 here, 2-way to represent 0 here. So it can explain it here. How can it solve problem 2-way 0? So you have to understand the process, right? Convert it into 1 complement, right? Convert it and add it to the number 1 of the number. And if the result is more than that means overflow, you have to discuss the last mode bit here. So think about this one here. Okay, and 1 bit. Yeah, exactly the same. Why do I have 2 slides? Yeah, exactly the same, right? You just convert 24. That's one. You insert more 3 bit and flip it and add to number 1. You have this one. 1, 2 complements cannot be done in the case of overflow. Right? So see, if you have 8 bits here, you have 8 bits that you have 8 bits. You have 8 bits. That means you have everything in the range of the 256 value. Right? But when you work with the negative and positive, you break it down in 2 halves. Right? That's why everything is range from 127 to the 127. Right? So that's good. It is overflow here. It cannot work with the 8 bit. So basically, you have to work with the 16 bit for this one. Now, come here. The 0 solution. Why? Why the 2 complements overcome the problem of the 0 solution here? Now, think about this one here. If I have number this one here, what is it? What is the number for this one? What is the number for this one? Yeah, that's 0, right? That's 0 here. So now see, if I have negative 0, what happened? This is the positive here. That is what I have negative 0 here. What happens if I want to represent in the two-word complement? Now you have the process, right? So you have negative 0. The first step, you have to find out what is the one complement, right? So see, you have 0. That means you have the 7 bit here. 0, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Right? You have one 7 bit here. Now, in order to find out the one complement, you have to flip it. Right? You have to flip it here. Right? So see, you have the number here. It's a negative, right? You have the one complement. You have 1, 2, 3, 4, 5, 6, 7, and 8 here. That makes sense? Okay. Now see what happened here. See what happened here. Now you have to add number 1 to this number. Right? You have to add the number to 1. The process is that you convert it and find out the one complement. Right? Add number 1. Right? So that's 1. When I add number 1 here, you have number 1 here overflow. I see 1 and 1, 0 carry out 1, 1 and 1, 0 carry out 1, 1 and 1, 0 carry out 1, so on, so on, so on. Right? That's why I have the number 1 here. It is overflow. But in the process is that whenever we have overflow, discard this. Sorry, discard. Remove this bit, right? So that's why I have to remove this here. So see the process here exactly the same, right? So see, even that I have the negative or positive 0 in the way of two complements, they are the same. They are the same. The way it represents the same. Make sense? Okay. So yes, that is a long process. To help you understand why the computer has to work with the two complements in order to represent negative number. It cannot work with the sign magnitude. It cannot work with the one complement. You have to work with two. Okay, that is a long way, right? That's a long way to go with the integer. So in the case of the floating point here, how computer represent it? So again, in the floating point, computer break it down break it down into two portions. You have the sign, negative or positive. You have the whole number, integer, and you have the fractional part of it, right? So you can think about this one here. If you have the 6.0 here, it is a floating point because you have the positive here, and you have the whole number, and even that 0 here, it is a fractional part here. So the integer part is that it is a whole number, right? So basically, you just convert it into the positive or negative. That's normal. That's the way you work it here. Now, that is the way you work with the integer part. It's very simple, right? You can work with one complement or two complement or whatever it is. It's very simple when you work with the integer part only. Now, what happens if you work with the fractional part here? So remember about the thing here. If I put the number 0.1, it's a decimal. So actually, this one it is a 0.1 here, right? This 0.1 here, 0.1. Actually, it has 10 raised to the power of negative 1, right? 0.1 is 10 raised to negative 1. Makes sense? Now, if you remember the process here, if you go back to the process of the column value here, the process of the column value here, where? Here, you go with the process of column value, right? So if you work a decimal system, it work everything value with the column value, right? So here, column number 1, number 2, column number 1, 10, 100, and 1000. And the reason is that 1, 10, and 1000 because it's by 10, right? By 10 raised to the power of 0. Now, you think about this one here. You think about after that, you have the fractional part after that, right? So see, for this one 0, 1, 2, 3. This one negative 1, this one negative 2, and this one negative 3, and so on. It works exactly the same. Right? So see, 10 raised to the power of negative 1. Actually, you have 1 over 10, right? 1 over 10. 10 raised to the power of negative 2, you have 1 over 100. And 10 raised to the power of negative 3, you have 1 raised to the power of 1000. Right? That's all. It works exactly the same for fractional part. So instead of increase 1, 2, 3, 4, now we decrease it negative 1, negative 2, and negative 3, and so on. Right? Okay. That is the process of the fractional part here. Now we come back to this one. Okay, that is the way you work with the decimal, right? And the way you work with the binary, it follows exactly the same. Right? You see now, if you look on this one, right? On the diagram here. So for this column, you have 2 raised to power 0. This column you have, and this column we have 2 raised to power 1, and 2 and 3 and 4. That is the integer part, right? That is integer part. But for fractional part also, you see for this one here, you have 2 raised to power -1, right? You have 2 raised to power -2, and you have 2 raised to power -3, and so on here. That's what you see. What happened here? 2 -1, you have 1/2. That means you have half here, right? 2 -2, that means 1/4. That's why you have the 2 and 25 here. 2 -3, you have 1/8. You have and you have there, so on here. Right? That's the process. When you work with the decimal, you have 0.1, 0.0.1, and 0.0.1, and so on. But when you work the binary, you have half, divide by 2, you have 4, divide by 2, you have 8, 16, and 33, and so on. Make sense? Okay. It works exactly the same rule here. Now, so yeah, that's the way it works here, right? So basically, when you have the fractional part here, the first one is 2 raised to power 2, 1, 2, 3, -4, and 5, and so on. And when you convert it decimal, 2 raised to power -1 is a 1/2, 1/4, 1/8, 1/16, 1/32, and 1/64, and so on here. All right? Okay. So think about this one here. So think about I have the number here. Now is this one here. I have the number. What is my number? Yeah, I have number this one here. Think about I have number. I want to convert a fractional part. I want to convert where my number? I do not have it. As you can, right? I have number here. 0.4, right? Now, if I want to convert fractional part 0.4 into the binary, how I do it here? It works exactly the same. Right? I have to work everything from the left to the right. So see, in order to make it up for 0.4, I do not need this one. That's why I put 0 here. So in order to make it for 0.4, I need 0.25 here, right? So when I need it, I put number 1. I put number 1 here. So when I have number 1, I have to minus it here. I have to minus 0.25, right? So I have the 15 left here, 0.15 left. I move to the left. In order to make this one, I need it because this one greater than this one, right? So I need it here. Again, I had to minus it. So I have 0.025. 0.025. I need this or not? No. No. Right? This one. And keep doing it until if you want to stop, how many fractional part you want. Right? So think about this one. You need 1, 2, 3, 4, 5, 6 to stop. Make sense? Okay, that's the process it works here. So see, if you only need the 6 bit after the fractional part, you stop it here, even that is not going to 0 yet. Okay. Okay, so basically that is the way you work with the fractional part, the way the computer store in the fractional part here. So we have to decide how many bits in the fraction part you want to store. 8, you stop at 8, 16, and so on. But the process is always follow exactly the same. You break it down in the column value, right? This one, -2, -3, -1, 2, 3, 4, 5, and so on here. And for each column, it has specific value: 1/2, 1/4, 1/8, 1/16, and so on. Make sense? Okay. So I think that's all for the first part of the module here. Because I have to go all over the way because you see in the homework you have to work something with number format. Okay, you have the discussion. Both by number, right? Also, we have a quiz with the by number here. That's why I have to come all over the process here to help you understand the process of sign magnitude, process of the unsigned number, sign magnitude, the process of the one complement, and process of two complement, and the process of fractional number. Okay, so I think now we move to the second part about the slide. Do you have any questions so far, guys? Any question? Okay. Okay, so for the number 3, it's understanding the structure. So in the number 2, you understand about the logic, that's the main logic. Now in the number 3, it's understanding about structure. So in this chapter, we learn about each advantage of unstructured spaghetti code, 3 basic structures, sequence, selection, and loop, using the programming input to structure a program. There's a need for structure, structure, and structuring and modularizing structure logic. Okay, you have the definition of the spaghetti code. Now, we need the spaghetti code is that when you just jump into the coding and you have the no plan, you do not make plan and just coding, and later on you see it's very confusing. Right? Some of them they overlap together, and some of them they have redundant. That is the point. The thing is the spaghetti code here. I think, but that's the process here that they give you the example of unstructured or spaghetti code. You see, they all overlap together. I see that's very confusing and overlap together. So basically, later on, when you work with the program, you break it down into 3 structures here. You have the sequence, you have the selection, and you have loop. But remember, they never ever overlap together. They can be netted inside each other, but they never ever overlap together. Okay, so basically for the structure here, the basic unit of the programming logic of each structure is one of the following. Whatever it is, later on, you know, for whatever program it is, even that is very, very complicated, whatever it is, you only have the 3 structures. You have sequence structure, you have the selection structure, and you have the loop structure, whatever it is. It only used in the 3 structure here, sequence and selection and loop, right? And you can combine them together, you can net them together. But whatever program it is, you can be construct from using one or more of the 3 structure here. So the sequence structure, it works one by one, right? In the sequence, one by one in the sequence. From the first statement to the second one, and go all over to the last statement in the order, from the first statement to the last one. Selection, it break it down into the branch, right? Break down the branch, and it check the condition. If yes, you do something. If not, you do other thing. Right? That's the selection. And the loop, you learn something about loop, right? The loop, that means you have you have the condition to check. If yes, keep doing it. If not, you terminate the loop here. Okay, and sequence structure, it performs action or thought in the order. It's always in the order from the first statement to the second one and that one here. You have no branching or have no skipping and in the selection structure, or sometimes they call it the decision structure here. It only asks a question, right? You ask a question. So it can take 1 or 2 actions based on the testing condition. So when you work the selection, and later on when you work the loop, you only have the testing condition, right? And in the case selection, if the condition true, you can do something. If not, you can do other thing here. Okay, so it's often called if then else, because it break it down into 2 branches here, right? So you have the condition to check. You have the condition to check. you have the condition to check. That's why you have the variable here to control. Right? If yes, you do something. If not, you do other thing. That's why they call if do something. If true, do something. Not true, you do the other thing. Right? Or the call it can be the dual alternative, or also can have the single alternative. And you have the loop structure. You have a repeat action while the condition remains true. Like again, you see in the zero code, right? You have many examples when you work with the loop here in the main body, right? So why the name is not equal, I just keep doing it, keep doing it, keep doing it. Yes, that is a flow chart in the case of the sequence. Everything works in the order. That one by one is the order. In the case of the selection here, it breaks it down into two branches. Right? If yes, you do something. If no, you do the other thing. Right? Okay, think about this one here. That is the case you work with the dual alternative, right? Dual alternative here. It contains the two alternatives, and that is the if and then else. So think about this program. Right? Ask you, what is your age? Right? What's your age? So from that, when you have the age here, that is the condition. Sorry. Okay. So when you got age from the user, right? You check the condition here. If age greater than or equal 18, you are eligible to vote. If not, you are not eligible. That's the way. That's when you work with the Raptor. It's very, very simple. And in the case you work the Python also, right? You see, you have age, you got it, right? And age in the integer format, right? And you check the condition. If yes, greater than 19, greater than or equal 18, you are eligible to vote. Else, that means less than 18. Else, that means less than 18, you are not eligible to vote. So when you look it in the pseudocode here, pseudocode, right? You have defined what is the age. It's a variable, right? You got it from the user here, and you check if the condition here, if then else if, that in the pseudocode. Now, so in the case selection structure, you can have dual alternative here, right? If true, do something. If not, do other thing here. But some case you have the single alternative also. That means true, do something, but not true, you just don't do anything. Just don't do anything here. So think about this case here. If employee belong to the dental plan, then deduct 40 from the employee gross pay. But if what happens if employee not belong to dental plan? What happens? Don't do anything. Don't do nothing here. Okay, so that is the case of the single alternative here. If yes, you do something, but no, don't do anything. Do nothing here. Now, with the loop structure is the repeat of the set of the action while the condition remains true. Again, in the loop, you only have the condition to check. If true, keep doing it. If not, you terminate it. Also, in the loop body, they call it the repetition or iteration. Iteration, that means every time you do for one time, the loop execute for one time. Right. So basically, in the pseudocode, you can see whenever you see the y or do y, you can see that is a loop here. I think about this one here, right? So this program, right, keep enter the number, right? Keep enter the number and enter the number 0 to exit here. So I think about this one here. It follows exactly the logic of mainline logic. I see that is housekeeping here. You have to get the number before the loop, right? You get the number before the loop and outside the loop, and inside the loop you check the condition here. You check the condition if true. But sorry, one more thing I have to highlight here. You have to remember when working with the pseudocode, when working with the Raptor, when you work with the Python here. In the Raptor, whenever the condition true, you exit the loop. But in the Python and in the pseudocode, if the condition true, you keep doing the loop. Right? That's why when you convert it from the pseudocode and when you convert it to the Raptor, you have flip it. You have to flip it here. So is that in the now we see if you look on when I work the Python here, y number not equal to 0, I keep doing it here, right? Keep doing it until I enter the number 0. But see, if number is 0, I exit the loop. Right? So again, that is one thing about the Raptor. I want you to keep it in mind. Right? In the Raptor, whenever the condition true, you exit the loop. But in the real programming language, if the condition is true, you keep doing the body. That's why when you convert it from the pseudocode to the wrapper, you have to flip it, the condition. Make sense? Okay, that's the thing. Okay, so for this program here, you see that you can think about it is housekeeping here. You get the my number here, right? So after that, when you go to the body, you have the condition here to check. Right? If not, I just double the number. Right? I print out the number here. See, you have the step to get the next number here. Otherwise, we can be indefinite loop. Right? And you can do the same with this one. It is housekeeping here. It is the main body here. And at the end of main body, I need to get the new number here to go over the new one. Right? That's why it is indefinite loop. Make sense? Okay, so in the loop structure, you have the while connect. That's the condition continue to be true. Do something, right? And why? Okay, so basically, again, for every program, you just use a combination of the three structure. You have the sequence structure, you have selection structure, and you have loop structure, and you can combine them together, whatever you want. So all logic problem can be solved using only sequence, selection, and the loop, and the structure can be combined in the infinite number way here. You can have stacking structure. You just put it on top of each other, or you can have the netted structure. You just put it inside each other here. So you can think about this one here, structure here for this one. You have the sequence, right? And you have the selection, and you have the loop here. That is stacking. They put on top of each other, right? So we see you have the loop, on top of that you put the selection, and you have the sequence of that. That is stacking. And in some case you can use okay, so in any individual task or step in structure can be replaced by a structure, and you have the netting structure. That means you place one structure within another one. Remember, when you put it within, you have to put it totally within. You cannot overlap it. That's the one I mentioned before, right? So when you work netted, you have to put it totally. So we think about, you put the loop, you have to put it totally inside the selection or inside the sequence here. You cannot overlap it. So the netting structure, you place one structure within another, and indent netted structure statement, and you have the definition of block. Block is a group of statements that execute a single unit. So it's asked here, what is the structure of this one? What do you think? What is the structure of this one? You have the sequence inside the selection. The sequence is the selection here. Okay. A sequence netted within the mixer. How about this one? Now you have to go in the right order here. What is structure of this one? What is structure of this one?
Selection.
So when you work with the netted structure here, right? You have to work it from the inner out. You have to work it from the inner. So we see for this one, you have to loop inside.
Selection.
No, inside the sequence here. Then see, if this one is sequence, right? You have the step number J and step number L. Right? So see, you have a put loop inside the sequence, and from that sequence, you put it inside the selection. Right? So basically, in order to analyze the coding, you have to work from the inner out. You have to break it from inside out. And how about this one? How about this one? What's the structure of this one here? What do you think?
So
That would be a selection inside a loop, inside a sequence, inside a selection.
Yeah, right. So basically, you see, you have the inner out, right? You see, the first thing here, that's the selection. Z is a loop, Z is a sequence, and Z is a selection. So we have the selection inside the loop, inside the sequence, and inside the selection. Yes, that is example of the some of the way you can net them together here. Okay, structure program has the following characteristic, includes only the combination of three basic structure. So basically, for every program, you only have the three basic structure, and you can combine them whatever you right? and each structure has a single entry and a single exit point with. That means you cannot overlap it. In that case, you cannot overlap it. And structure can be stacked or connected to one another only at the entry or the exit only. That's it. That's why they call it a spaghetti code here. They call it spaghetti code here. See, they totally overlap together, right? They overlap together. And exit of this one is inside another one. It's not good way for when I work with this one. Okay, so using the priming input to structure a program. I don't know why they have so many definitions here, but you can think about the priming input here or prim bit. It is the first input of data record. You can think about prim input. It's the same process when you work with the housekeeping. That's the process you need to get ready for the program. Need to get it for program. Right? It reads the first input data record. Right? See, it's outside the loop. Right? Outside the loop and before the loop here. So you can think about from my definition, from my understanding here. The priming input, you can understand it works exactly the same with housekeeping. It is a step outside the loop, before the loop, and it needed in order to get ready with the loop in order to run the loop here. Right? Have the keep the program structure, analyze the flowchart for structure one step at a time. Okay. Now watch for structure loop and go not follow this order. So whatever first question, take that later. Okay, now think about this one. What's wrong with this program? What's it? What's wrong with this program? If you look on this program, what's wrong here? You can think about not EOF here. You can think about not and a file. Right? So think about you have many you have the file. You have many records here, right? And you read from the first one until the last one, and the last one that means and a file. Keep doing it from the first one until the last one here.
It's just a continuous loop. It doesn't give you a chance to exit it.
Yes.
There's no input for the original.
Yeah, right. So this one, what happened here? You have original number, right? You can think about this one here. What is it? You have original number. You have the input number 2 here, right? So see, keep doing it, right? So see, I don't know why it's quite confusing for the slide here, but actually it should do better with this one. So we can think about this one here. I do not use this one. It's very confusing, right? So think about I have an original number. Number here. Not equal to 0, right? So think about this program. Keep asking user enter the number, right? Enter the number, and for each iteration, look that double the number and print out the number here, right? Keep doing it here. So, but yeah, you are right. For this one, you will go with indefinite loop, right? Because you see, if you enter the number 10 here, what happened? Check not equal to 0, right? Print it out. Number 20. So what happened? Go back 10 again. Print out 20. Go back 20 forever. Right? So that what happened here? How we correct this one? How we correct this problem?
After output, put another input of
Yes, you need to get a new number, right? In order to control, to exit the loop here. So basically, for this one, again in the loop, you have to copy the process and you have to put here. Right? So you see, the work exactly the same with the mainline logic here. You can think about it is prime input or you think about housekeeping it. It works the same, right? You check the condition, and inside the body loop, you have the action to change the variable with otherwise indefinite loop. Right? That's why not logic here. You're missing that. That's that. Okay, that's also they do not recommend you to do. But so basically, for the prime logic and the housekeeping, you have to bring it out of the loop, before the loop, right? Before the loop and out of the loop. And so for this one, Okay, that is the correct one here. That's it. You can think about that, the primary input, right? And see this step here for all subsequent input. You only need a step in order to control how to terminate the loop. Otherwise, you can go indefinitely, right? Okay, this one not right. This one because you do not have a primary input before the loop here. Okay, so you structure programming for clarity. You have the professionalism, efficiency, maintenance, and modularity. It's easy to break it down into module. What else? Recognizing the structure, very simple. I do not want to go to this one. Oh, so okay. So I think that's all for today. So here again my policy, right? I expect that if you come back, you can see about you can read about the book, or you can watch again about the recording video, or you can see about the slide, whatever it is. But I hope that you have to prepare for the assignment, right? So on Thursday, if you have any question with the homework assignment, you can raise to me on the class, right? Okay, so that's a better way. At least you have some preparation, so we can work together. It should be better instead of waiting problem. So, do you have any question, guys? Jaden, are you here?
Yeah.
Quantum, are you here? Eric, are you here?
I'm here.
Joe, are you here? Devin, are you here? Lindsay, are you here? Michael? Matt? Mallory, are you here? Mallory? Bill, are you here? Hunter here. Zaire, are you here? Max, are you here? I think he's here, right? Yes. John, are you here?
This is John.
Yes. Paul, are you here? Paul.
Here.
This one. Daniel. Here. Parker. Carl. Are you here? Alex.
Here.
Drew. Here. Okay. Tucker. Tucker, are you here? Look here. Marcom, are you here? Marcom. Okay, so I see you guys on Thursday, and remember that you should be better you prepare something about the homework assignment, right? And you can raise any question to me on Thursday. Bye bye, guys. Bye.